This is the 29th video in a class on single agent search. And in this video, we're going to move slightly away from heuristics for a moment. But what we're really going to do is we're going to look at where the branching factor comes from in a state space. And what that's going to allow us to do in the next video is then actually to look and see what is the impact of a heuristic. There are quite a few different predictions that were used to try and say what the impact of a heuristic is. And so the analysis we have here is going to come from the pattern databases that historically this work followed from the pattern database work. And it shows what the impact of the heuristic is. But we've been looking at here, so if we're thinking about a state space, we've always been thinking about a branching factor of B, and then usually we have a depth of D. And the question we're trying to answer today is where does this B come from? Okay. Sorry, someone messed around with my my kids were playing with this. There we go. Okay, where does this branching factor B come from? And and we might think that just comes from the state space and that this is partially true. But we're going to show here how we can analyze the branching factor as we get to a really large search and what happens with the branching factor. And we're going to look at two different domains to do this. We're going to look at the Rubik's Cube, and we're also going to look at the sliding tile puzzle. But we'll start with the sliding tile puzzle because it's a little bit easier. And in order to do this, let's start out by looking at the a very simple puzzle. Well, actually, we can start really simple. So if we think about the 2x2 sliding tile puzzle, it has exactly one blank. And so if we are a little bit naive about this, we'd say, well, what is the branching factor? Well, the blank can move two locations in each time step, and therefore the branching factor might be 2. But if we think about that when we're doing any search, in the first step, there's 2 possible actions. But after that, we really don't want to go back to our previous state. So once the blank's moved here, the only other action we're going to get is to continue to move forward. Okay. So for the 2x2 sliding tile puzzle, if there's no parent, we're not allowing to go to the parent, then the branching factor is 1. If there is a parent, we allowed to go back to our parent, then the branching factor is 2. And that's really easy. Okay. But it ends up that it gets quite a bit more complicated when we go into when we go into other puzzles. And oftentimes I ask students to sit and think about this problem before we actually work through how this is done. And think about, like, how would you solve this problem? So this is the 2x2 sliding tile puzzle here. And that answer was really easy. But let's think about here the 3x2 or the 5 puzzle. Okay. And what this looks like is something like this. So that the goal state would be 0, 1, 2, 3, 4, 5. And if we're looking at this, then we might, for instance, say, let me say, I encourage you to pause the video right now. Think about what the answer might be. What do you think the branching factor might be? And see if you're able to come up with the right answer. So I'll give a pause for that. And then the most likely answer that might be sort of the first thing you think of is, well, we'd say, look, we could have the blank. The branching factor depends on the blank would be the first observation. And the blank can be in 2 different locations. If the blank is in a corner, then the branching factor there, and let's ignore parents for right now, just to make it simple. So we might look and say, well, in the corner, the branching factor is 2. And we might look in the middle, which would be these locations. And in the middle, the branching factor is 3. And so if you look here and say, well, there are 4 possible locations for the blank to be in the corner. There's 2 in the middle. And so what we can say is 2 out of the 6 locations have a branching factor of 3, and 4 out of the 6 locations have a branching factor of 2, and you might say, therefore, the branching factor is 2.33. But there's actually a problem with this analysis. And the problem with this analysis is that this makes the assumption that the blank is equally likely. So this is what is being said right here. It's equally likely to be in any given state, and therefore the probability of being in, for instance, a middle state here, which is these two states, is equivalent, or it's in just sort of 2 out of 6, there's 2 of them, so that's a uniform probability. 4 out of 6, there's 4 corners, and therefore we say there's a 4 of 6 probability there. And it ends up that that's not the case. So I need to say this isn't the way that you want to do the calculation, because this gives you the wrong answer. This won't give you asymptotically, it won't give you the right answer, because in practice we're actually not equally likely to be in any given state. And what we want to do instead is we want to think about what happens in the steady state of a really large search. Okay, so we have Okay, so for steady state, of a search, what's going on? In the steady state of a search, what you can imagine here, and we'll just use 3 here, for instance. So let's just say we have 3 different types of states that each have different branching factors in them. And so that would be, in the sliding tile puzzle, we might be thinking about corners and middle states. So corners and middle states, but we could imagine that there's more than that. And so the idea would be is that, look, if I'm going to have a branch, if I actually have an asymptotic branching factor that is going to be the same once I get far enough into the search, what's going to happen is there's going to be some breakdown of different states. So maybe type A, some type B, and some type C. And what's going to happen is if I apply my successors to these states, to all the states that are in type A, all the states in type B, all the states in type C, what I'm going to do is I'm going to end up being in a set of states. What's going to happen is the number of states, so it's going to be B times more states. Number of states is going to go up by a factor of B. That's my branching factor. But what should happen here is that if we expect that there actually is a branching factor to be found, some expected branching factor here that I could use for B to the D, then I would expect that the number of the fraction of states of each of these classes here would actually, this fraction would stay the same. So the idea is I've got a whole bunch of states in my state space, and I expand them all. They generate successors, maybe of all different types here. And when I do that process, I'm going to end up with many, many more states. But the fraction of states of each given type, these ratios here, are going to stay the same. Okay, and so this is the model. This is the model we're going to use that basically says, hey, assume that I search really, really deep until I get to a point where the branching factor does become a constant. And then I'm going to look between 2 layers of that state space. I want to know what that constant is, and it's the only way that it can be a constant is if these fractions stay exactly the same, the fractions of my different types of states. Okay, so that's the this is sort of the big idea that we need to understand in order to understand the analysis that we're going to do here. Okay, so this is the wrong analysis, and we'll set that aside. Okay, that's done. I like my shadows here. Okay, so now we're going to do the 3x2 5 puzzle, and we'll do it in the correct way. So what we're going to do, as I suggested before, is we're going to have 2 types of states. And the 2 types of states we're going to have is we're going to have corners, so I'll call them C, and we're going to have middle states. and just say there are 4 corners and there are 2 middle states here. But we want to know, we're doing it now without, this is with parents. What I want to know is what are the rules for these types of states and the types of states that they generate. And just to say that this analysis here was done in a paper by Rich Korf, Reed, and Edelkamp. Stefan Edelkamp wrote a textbook on heuristic search. It is a large volume, has a very comprehensive details on heuristic search. And so if you're interested in really getting into a lot of data structure details and other things like that, that's a great textbook for that. Anyway, so it's going to give us what's called the Kre analysis, and in order to do this analysis of heuristics, they started by looking at our branching factor. Okay, so we have types C, which are corners. We have types M that are middles, and we have different numbers of those. And what we're going to ask is, what are the generation rules? So for instance, if I have a middle state, what are the successors going to be in the next layer? Well, if I have a middle state, what it's going to generate for me is it's going to generate 2 corners, and it's going to generate 1 middle. I could put a plus here, but we have to be careful about this. This is what, I'm not necessarily adding them together, but these are really the types of what we're generating. Where if I have a corner state, so sorry, just to show you here, if I have a corner state, it's going to generate 1 middle and 1 corner. A middle generates 2 corners and 1 middle. So I'm just thinking of, and all the corners are the same. So right, corner gives a middle and another corner here. So corner is going to give me a middle state. Actually, I'll write a corner state and a middle state, 1 of each. And so we want to think about this process, and we're going to use it to determine the branching factor. And just to say that we're going to now reason about what happens here. And if you have trouble following this, I've done this before. I'm not going to do this sort of in the online video, but you can just write a little program that generates states in the sliding tile puzzle. And you can keep track of where the blank is, and you can label them as being middle states and corner states. And you can actually run this program and watch the fraction of middle states and corner states that you have when you expand them. And you can watch, and you'll actually see the calculation, that it'll converge to the calculation we're about to do here. So we can actually run this in practice. We can see what it does, and then we can ask, well, what is the math that we're going on here? And the math, what we're trying to say here now is we want to go back to these equations, and we're thinking about, okay, from this layer to the next layer, the number of states went up by a factor of b. Okay, and so what we want to say here is for every middle state, and there's there's multiple ways we can look at this. So, but for every middle state that existed at this layer here, then we're actually, because this has grown by a factor of b, what we expect is the fraction of middle states from one layer to the next is going to grow by a factor of b. But in doing so, what we're going to get is we're going to get some fraction of, I have to be very careful here. What we're asking is, where do my middle states come from? Okay, where do my middle states come from? Well, my middle states, so I take the number at the previous layer, I multiply it by b because that's what's going to happen from this layer to the next. And then I'm going to ask, if these were my middle states, where did they come from in the previous layer? And the answer is I got 1 middle state for every middle state, and I got 1 middle state for every corner state. So what I'm going to write here is the fraction of middle states plus the fraction of corner. Because in the next layer, or when I'm looking at this fraction of corner and the fraction of middle states, that number together will give me it's essentially giving me the number of new states, which is b times larger than the fraction of middle states I had at the previous layer. Okay, let's write this out again. So now what we're doing is we're thinking about the fraction of corner states. So b times the fraction of corner states. Where do corner states come from? Well, I get one corner state for every corner state, and I get two more for every middle. So what happens here is I get 2 times the number of middle states plus the number of corner states, or the fraction of corner states. So what we're asking here is the number of corner states at the next level, where did they come from? Well, I got 2 for every one that was a middle state, and I got 1 for every corner state. And when I add these together, they're going to be b times larger than the number of corner states, or the fraction of corner states that I had the previous layer. Similarly, where did my middle states come from? Well, they came from, I got 1 from every middle state, and I got 1 from every corner state. So this is going to give me, but this is going from like one layer to the next. So at the next layer, there's going to be b times more, which is the number of middle plus the number of corner. The other thing that I know is because these are fractions, so I know that the fraction of corner plus the fraction of middle is equal to 1. Okay, so this is just telling me how does these ratios grow. What we see is what we're writing here is basically how many states are there at the next level. So like if I take some type A and I go to the next level, there's for the type A, well, they're going to come from however many were created by A, B, and C. And so that's going to tell me, there's 2 ways we can think about it. We know it's going to grow by a factor of B, so it's B times the number of A, plus it's however many came from A, how many ever came from B, however many came from C. So this says, look, there's B times more, and there's also where did they come from. There's B times more, and where did they come from. And finally, they have to add up to 1. So now we have 3 equations. We have 2 unknowns. And so we can, we have 3 unknowns because we don't know what the branching factor is. So 3 equations, 3 unknowns, we can solve this. And I'm going to just pause the video really quickly. I'll work out the math, and then I'll turn it back on. I'll show you what the math is, just because the math is a little bit boring, and it's just basic algebraic manipulation. But let me do that. We'll pause it, or I'll be back instantaneously, and then we'll look at what the actual value is. Okay, so we're back, and let me just show you really quickly. We take this first equation right here, m plus c, and we know it's equal to 1. So we know f of m is equal to 1 over b. We then take the second equation right here. We substitute 1 over b into for m, and we find out that f of c is equal to b minus 1 over b. We then take our third equation, and we substitute for f of c, f of m, and f of c to get the entire equation in terms of b, which gives us this. When we work it out, it gives us a quadratic equation, and then we can write this out, and we see that the answer is 1 plus or minus the square root of 2. The branching factor cannot be negative, so the answer is that the branching factor is 1 plus the square root of 2. And so what that tells us is that the overall branching factor is not, as we were saying before, is not up here. We thought maybe the branching factor was going to be 2.33, and instead the branching factor is, so the square root of 2 is 1.414. This is 2, sorry, is equal to 2.414. Okay, and so this, what this says is that we would have been off if we tried to use this value, just as of course I said we would, but the true branching factor, the state space, is 2.414. And what does that tell you? Well, in the middle state, the branching factor is higher than in the corner states. And so what we're seeing here is we must be spending more time in middle states than in corner states. And that's because the branching factor is higher there. So we're going to get out of our corner states more quickly and get back and spend more time in our middle states. Okay, so this gives us the branching factor, the exact branching factor. So we've finally done it. We've given you the answer. How do we compute the branching factor? And it's by this process of looking at this fraction of states and how they grow for the sliding tile puzzle. And this, I'm going to go through this process again just so that you can see it again. Of course, the algebra isn't necessarily the interesting part, but the process here of writing down these equations, and let me just write down, so the last equation is b is equal to 2.414. And that gives us, with this math, I'm just going to move the math to the side. But given that we can do this math, then we can compute the branching factor of a state space. And this is how we're going to do it. And this is actually really important. We're going to get back to this a little later. We're going to talk about constraints. And if we can, constraints are reducing the branching factor. And for instance, if I say that I don't go back to my parent, this is a constraint. I'm not allowed to go to that space, that state. And so reducing the branching factor is very powerful, and we'll see what the effect of the heuristic is. So let's do again now the 3x2 sliding tile puzzle, and we're going to do it without parents. So we're going to do parent pruning here to try and get rid of them. So now what's going to happen? Well, if we try to look at the same problem without our parents, the problem does get a little bit more complicated. And the reason why it gets more complicated is I have to think about how did I actually get somewhere when I did my calculation? Okay, because what can happen here is that I can be at a middle. As before, I could be a middle or I could be a corner. But I could be a middle because how I prune my parent. So if I go from a corner to a middle, then my middle is going to generate another corner and another middle. If I go from a middle to a middle, I'm going to generate two corners. And so what we see here is that by pruning our parents, we need to know where we came from, because that's going to change the way that we generate our successors. So what we're going to have is I'm going to label these, and I'm going to use two letters to do this. So what we're going to have is if I'm in the middle and I've come from the middle, then what is that going to generate? Well, in the middle, I've come from the middle, then I'm going to generate two corners, and those corners come from the middle. So I generate two corners coming from the middle. So just to be clear here, this is the from. Okay, and then what I'm going to say is, well, what about if I'm in the middle, but I came from a corner? So I came from a corner into the middle. Well, now I'm going to generate a middle from a middle, and I'm going to generate a corner from a middle. So this is going to give me a middle from a middle and a corner from a middle. Okay. The next thing that I'm going to think about is corners. So if I'm in a corner right here, then I have a corner and I've come from a middle, let's just say, then what I'm going to generate, well, the only successor I have is a corner. So a corner coming from a middle is going to generate a corner coming from a corner. And the last thing that I want to look at here is a corner coming from a corner, and that's going to generate a middle coming from a corner. So a corner from a corner is going to generate a middle coming from a corner. Okay. And now what we're going to do is the same thing we did up here. So basically for each of the types, we now have 4 different types. And for each of these types, we're going to write down 4 equations that have to do with the growth of the state space. So the state space grows both by multiplying the previous fraction by b, that's how many states I expect, or then times the constant. I mean, if we wanted exactly the same numbers, to think of it in terms of states, there'd be some constant times here, and the constant times here, which is the number of states. But we don't have to worry about these. So the number of states here is going to grow by a factor of b. And then this is another way of looking at, which is where are they coming from in the state space. And with this more complex set of rules here, we'll see this a little bit more clearly. So what we're going to have here is we want to think about the fraction of states that are in the middle coming from the middle. And so those we expect just to grow by a factor of b as we go from one layer to the next, but they're also going to grow by these expansions of states. And so the question is, where do middles come from? Well, it ends up they only come from one place. They come from middles of corners. So this is going to be equal to the fractions of states which were on the middle coming from corners. Now we have the fraction of states which are on middles coming from corners. And where do they come from? So we want to look here, no middle corner. Actually, it only depends on corner to corners. So the fraction of states which are on middles coming from corners depends on the fractions of states which are on corners coming from corners. The fractions of states which are on corners coming from middles. So let's take a look at that. They're coming from middles, so of course they have to be coming from one of these. And so we get 2 corners from middles from here, and we get 2 corners of middles from here. And so what it's going to be is it's going to be 2 times the fraction of mm, because every mm is going to give me 2 corner middles, and then 1 times the fraction of middle corners. And finally, we have the fraction of corner corners. And where do corner corners come from? They come from corner middles. So this is going to be equal to the fraction of corner middles. And then we know that the fractions mm, mc, cm, cc, sorry, those are getting larger there, adds up to 1. And so what we have here is we have 5 equations. We have 1, 2, 3, 4 plus the branching factor, 5 unknowns. And so we could just sit down and we could solve out these equations by basically solving for each of these values, substituting in until we get rid of all the fractions and only have b. And if we do this, we're going to get b is about equal to 1.35. Okay, so this is the 3x2 sliding tile puzzle. And this is how we get it. And I won't work out the algebra here. It's good exercise to see if you can work that out. But it's just, solving equations there. Okay, so if we look here, what we saw is a naive view of the branching factor was 2.33. If we were to remove our parents from there, I believe that would be 1.33. Then what we see is the 2.33, if we actually calculate what it is, it's 2.4. 414. So the branching factor is a little bit higher here. And what we see here is 1.35 if we remove our parents. So there's actually, it's worthwhile to look at like what is, if I think I'm searching depth 10, what is 1.35 to the power of 10 versus 2.44 to the power of 10. There's a very significant difference there. And so that just gives you a sense what the power of reducing the branching factor is, and the power of doing things like removing parents from the search. So that is a very, very important thing to do if you want the search to be effective. And if we look at this, then this should give you a fairly good sense of what's going on here. Basically, we're modeling the growth of the state space, and this gives us this picture. We've seen the picture of the by puzzle, both by not removing parents and removing parents. It's the same process. But just for the fun of it, what we want to do is we want to think about now the Rubik's Cube. Okay, and Rubik's Cube, I still have my Rubik's Cube sitting here. So Rubik's Cube is interesting. What we have here is we have 1, 2, 3, 4, 5, 6 faces. A cube has 6 faces. And so if I were to be naive about it, or the simple answer to this would be, well, there's 6 faces. And then the question is, how do we count our actions? And so there are different actions. There's a quarter turn metric, which means that every turn counts as 1 turn, and there's no half turn. But there are, maybe the more common metric is saying that it's 1 action to turn 90 degrees, 1 action to turn negative 90 degrees, and 1 action to turn all the way around. And so that means that there are 3 possible actions we can take. So 6 times 3 is equal to 18. So that's the naive version of the Rubik's Cube, if that's the case. But it ends up that we can do better than that. And this is very important. It's, of course, one of the things that we can do to try and improve things. So we can try to do better than that. And what we might say is, well, look, here I have, for instance, this face. And if I move this face once, then clearly I don't want to move that same face again. Okay, so certainly we could start out clearly like, actually, I can remove my parent, right? So I could go from 18 to 17 by removing the parent in a naive way. But I can do better than that. That says, in one move, I can reach any orientation that I want of one particular face. So once I've turned that face, there's no need to turn that face again. So this would say at the very beginning, there'll be a branching factor of 18, but we could do better and get to actually to 15. So if we just remove the parent, we're going to get to 17. If we do the parent face, then we can get this down to 15. But what we're going to notice is that actually there's other types of symmetry that can occur in Rubik's Cube, and we'd like to do better than that. And what we're going to think about is if we think about the other thing that can happen here is that I have a face. So right now, let's see, yellow is opposite to my white face. And so if I rotate this yellow face here, after I've done that, I can turn my white face and it's totally independent. I can do those, in particular, I can do those in any order and they don't impact each other. And so I don't want to think about like, well, moving the yellow face and then moving the white, or moving the white and moving the yellow, or particularly moving the white, then the yellow, and then the white again. That would be really bad because I would get back to allowing some of these actions that I shouldn't allow. So what we're going to do is we're going to call some faces to be first faces, and then we're going to call second faces to be the ones that are opposite that. This is a little bit hard to draw here, but I'll try to do my best here. And actually, I'm going to use a grayed out color. So the idea here is we're going to label this a first face. We're going to label this one a first face, and we're going to label this one a first face. And the idea then is sitting behind each of these, opposite each of these, we have this other face here. And this face, these faces, I can't do my S's as well in perspective, but that's a second face. Over here, we have a second face. And sitting back here, we have a second face. Okay. So again, looking at the Rubik's Cube, we're going to have three faces, which are, let's just say it's white, blue, and green, are my first faces. And if I'm going to do a face and then its opposite, then I'm going to have to do the first one first. I'm not allowed to do the second one first. Okay. So what does this look like? Okay, so let's think about this. What we have is we have first faces and second faces. So if I am writing this down, the question is what happens when I move a first face? Okay, when I move one of the first faces, I'm not allowed to move the first face again. So this is going to, after this, so if I move this face right here, I'm allowed to move this face and I'm allowed to move this face afterwards, but I'm not allowed to move this one. Okay, so I get two faces. Each of those faces has 3 possible moves. So I'm going to get 6 possible first face moves when I'm done with that. And then when the other thing that I'm going to get after that, now it is possible that I will want to, for instance, move this face and then move its opposite face. I just have to do it in the order. And so I am allowed to do a first and then a second. It's the second and then the first I'm not allowed. So after I've done a first face, I can actually do any of my second faces. If I think about my second face, well, if I've done a second face, let's just suppose I've turned this one, then I'm not allowed to do the second face again, and I'm not allowed to do the associated first face because I've said they have to be done this one and then this one. But after I've done this second face, I can do this one or this one as much as I want. So what we see is, okay, I've done a second. I'm allowed 2 firsts. Sorry, let that disappear. I'm allowed 2 firsts, which is this one and this one. And I'm allowed 2 seconds, which is this one and this one. Each of those has 3 moves. So I'm going to get 6 front faces and 6 first faces and 6 second faces. And then if we write our equations down, and then remember here, so I'm saying what is the fraction of states? So I want to know B times the fractions of states that are first states. Well, where did they come from? They come 6 from the firsts and 6 from the seconds. So this is equal to 6 times the fraction of firsts plus 6 times the fraction of seconds. And then branching factor times the fraction of seconds is going to be equal to, where did the seconds come from? Well, I got 9 for every first face. So it's going to be 9 times the number of first faces. And I got 6 for every second face. So 6 for every second face. Okay. And just to say, there's a tendency to try to write these equations in terms of like these direct um, generations, like what's actually being generated here. It looks a little bit like a recurrence, and that's not the right way to do this. We want to think about at the next layer. So this is the current. This is the next. And we want to ask, where did the ones at the next level come from? Where did they come from? Well, the firsts came from 6 firsts, and they come from 6 seconds. Where did the seconds come from? They came from 9 seconds and from 6 firsts. And as before, we know that the fraction of firsts plus the fraction of seconds is equal to 1. And I can solve for these fractions. It ends up that we spend about fraction of first is about equal to 45% of the time, and the fractions of seconds is about equal to 55% of the time. And so overall, if we think about this branching factor, I'm spending more time in these states than in these states. So these states are generating 15 successors. These are generating 12. And so what happens in practice is I get my branching factor is equal to 13.3487. Okay, so again, I just didn't do the algebra here to work this out, but we had 3 equations and 3 unknowns. So this isn't, hopefully that's not a hard step to do, and you should be able to validate and solve for each of these numbers. So what that gives us is now we have a method to be able to take a state space, and if the branching factor does converge on a particular value, then we'll be able to compute what the convergence is, and that will give us the asymptotic branching factor. And so now we finally know in our b to the d that we've been talking about for exponential state spaces, then this is the b that actually comes out of it. And so that's really useful. That's been a foundational piece that we've had so far. And we're going to use that then in some of the other details here to be able to predict what happens, what is the effectiveness of a heuristic, how does it actually impact the search in practice, and we'll look at that in the next video.